Well, so far we have done that up to uniaxial bending, axial loaded column and uniaxial bending. Now, what about say biaxial bending? How shall we do the biaxial bending? That if the section is having in both ways, that means axial load Pu mu x and mu y. So, Pu mu x mu y, that is given. Then we have to find out a suitable section along with that percentage of steel. So, we have to find out the percentage of steel and the suitable section. What happens here, if we have say x, y and z, I think we have done something wrong. Anyway, so what we can do it here, I think let us make it this is x, this is y, then we can follow the same coordinate system. So, x, y and z, what we can do, the section having say something like this. This is the interaction diagram about one axis. Similarly, about the other axis also, it can have something like this. And we are having, because mu x and mu y, we can have the resultant also, that way also we can find out. So, the curve may be say something like this. It is just say one say in 3-dimensional I am talking. When I am talking this particular one interaction diagram, it is difficult to get in 3 dimension. So far we have done for uniaxial that say moment and force interaction curve, that we have got it, and that is given in SP16 also, and one can make on your own also. That means you can develop on your own. There is nothing say great thing, you can develop your own thing also. Anyway, that we shall come later on. What I am trying to say, the curve you are having along this axis, that means y and z axis, so we are having this one interaction curve. Similarly, z and x axis here, that is also another curve. That means in another axis somewhere I can get another one. So, like that I can make so many interaction curve. That means as if you can consider this one as if that you are taking 1/4 of an onion, as simple as that. If you take that onion 1/4 and you are cutting vertically, so that portion, you imagine that shape which you will get it as a say interaction curve or interaction diagram in say 3 dimension. So, when you get that one, that means now if you know mu x, mu y and pu, there are 3 parameters now, and I have to find out a section along with the area of steel, so that I can say the section is safe. For that, what we do, so this is that one obviously biaxial bending. What we do, how shall we design it? We design it in a fashion, let us make it this way, that given, let us first find out, given Pu mu x mu y. Please note, we are talking say design load. When we shall generally it happens that P is coming from the top, say bending moment also coming at the column junction, that all those things are coming, P also coming the actual load. Now, after multiplication of 1.5, all those things, including the self weight of the column also you have to take. So, then finally it is coming as a Pu. Okay. So, that mu x, mu y, all those things whatever way it is coming. So, as if we are the final form, but when you will do the actual say your analysis, for a particular structure analysis, there you have to take care, say self weight, lot of other things, load calculation, you have to take it. Anyway, so let us take say Pu, Mux, Muy, that is given, that steel grade specified by say Fy, concrete grade specified by FCK, clear cover that is also specified. Now, what we have to do, choose a suitable section. Choose a suitable section and let us say B times D. Also choose percentage of steel. So that is say P. So these all those things are given or assumed. Clear cover we can assume 40 millimeter or 50 millimeter, whatever we give. So let us say that we shall give for all the cases we shall give 40 millimeter. Anyway, but others are specified, we have to take 40 millimeter. So now choose a suitable section B times D. Here in this case you can say as if you are doing the analysis rather than design, compared to your say beam or slab where you are providing the section, you are calculating the say effective depth and then you are providing a section. But in column design you can say, analogous to that I can say that here at least as if I am doing the analysis part. That means I am taking all the things and then I am checking whether that my trial section is correct or not, whether it is safe or not. That is what I am trying to do it. So you are choosing a section B times D, choose percentage of steel also and compute P by FCK. What we can do now, since if I know Pu, since I know Pu, for a given Pu and P by FCK, find, and also D dash by D, find Mux1. What does it mean? It means that Pu is given. I have already chosen P by FCK and also I know D dash by D. That means I can go to a, since I know P by FCK, D dash by D, also I know Fy. Fy is that steel grade. So since I know Pu, P by FCK, D dash by D, Fy, so I can go to proper chart of SP16. And then what I can do, since I know Pu, so for that P by FCK I can find out what is the maximum that uniaxial bending, that one how much it can take, that also I can find out. So I can calculate Mux1 also. That means if the Pu is given, so I can find out the maximum uniaxial bending about that particular axis. So that is your Mux1. Similarly, I can find out for given the same Pu and P by FCK, D dash by D and Fy, find Muy1. So that means I can find out about the other axis. So what I can do, if this is your section, B and D, so I can find out for find the what I have told Mux1 and Muy1. Not only that, I can also find out Puz. What is PUZ? PUZ is the maximum axial load capacity of the column. The section you have chosen, what is the axial load capacity, that also I can find out, that is your say PUZ. So that means when I am choosing a section and the area of steel or P by FCK, on the basis of that I can find out MUX1 for a given PU, MUY1, also that PUZ, the maximum axial load capacity. That means all of them I can find out. So if I get that one, now I shall do a check. What is the check? The check is MUX by MUX1, MUX by MUX1 to the power alpha n, MUY by MUY1, sorry, Y1 times alpha n should be less than equal to 1.0. What about this? I know MUX, that is given, for that I have to design. I know MUY, for that I have to design, and MUX1 I have got it from the proper chart with d dash by d, Fy, all of them I have got MUX1, I have got MUY1, but I do not know alpha n. What is that alpha n? Alpha n is dependent on PU by PUZ. I have already computed PUZ. So PU by PUZ and alpha n. If PU by PUZ less than equal to 0.2, then alpha n will be 1, and if it is greater than equal to 0.8, then this one will be 2.0. So I can say the curve looks like this. This one will be your PU by PUZ, and this is your alpha n. I can find out somewhere here. Let us say this is your 1 and this one is a 2. So curve comes like this. This is your 2, this is your 1. So, and this is your 0.2 and this is your 0.8. The curve that say your, that means this is the interpolation, you can do it. That means if it is less than equal to 0.2, it is 1. If it is greater than equal to 0.8, then it is 2. In between that you just simply linearly interpolate that value of alpha n, the value which you have to put it here. But what about your PUZ? PUZ equal to 0.45 FCK AC plus 0.75 Fy times AS. This is your PUZ. So PUZ also I know, PUZ equal to 0.45 FCK AC plus 0.75 Fy AS. This is the one. So I know everything. So that means the biaxial bending, for that the design is very simple. What you have to do, that you find out MUX1, MUY1 for a selected value of say your percentage of steel. Then you find out PUZ, find out alpha n on the basis of PU by PUZ, and you find out using this equation less than equal to 1.0. If it is less than equal to 1.0, then you just stop. Otherwise again you have to change the section or percentage of steel, and then again you have to do your calculation. That's all what we do it in say your biaxial bending. Okay. So I think we can try one problem, very simple problem that we can try and we can find out. So let us take one example. So rectangular column, okay, one thing I think I should tell, this one, because I am telling so far that SP16 this one, but where is that in IS 456, that clause, I think I should refer that one. So that one you will get it in clause last one. So clause 39.6, page 71, IS 456 2000. So please note this clause 39.6, page 71, IS 456 2000, where you will get the whatever I have told this particular one. Okay. So let us take the column section, size of column. (400 by 500), concrete M20, steel Fe415, PU, let us take again, okay, 1200, MUX, let us take 100 kilonewton, MUY, let us take 80 kilonewton, clear cover 40 millimeter. Okay. So, and we shall try, let us try with the 25 millimeter bar. Steel bar dia. So, what we can do it here, d dash by d, let us compute d dash 40 plus 25 by 2, 52.5, and we have an percentage of steel. Let us take percentage of steel. Shall I take 1.5%? So P by FCK equal to 1.5 by 20, or we can do some tricky thing, I think. That what we shall do, let us take a section, we shall go little far, and what is our that you would say SP16 says. So our that chart will start from, we shall assume that we shall provide the reinforcement in all four sides, because we are talking say your biaxial bending. So we shall provide the reinforcement in all four sides, and what we can do this one, that our chart starts from chart 43, 44, 45 and 46. These are the four charts. So let us write down here chart 43, 44, 45, 46 for d dash by d equal to 0.05 to 0.2, for Fy equal to 415 Newton per square millimeter. We shall provide this one. Now what about the tricky thing, what I am telling here, 1.5 by 2, 1.5 by 2, it means it will be 0.075, but what happened here, that in this SP16 it gives in 0.02, 0.04, 0.06, 0.08 in this fashion. So that's why I am telling. So let us take, instead of taking 1.5%, let us take 1.6%, because we are assuming, so it will be little bit easier. So I can take 0.08. That means I need not, again I estimation all those things, I need not do it, because directly I shall get one curve, that is P by FCK 0.08, that curve I can choose it. I can take it 1.4 also, so that way this tricky thing I am doing here. So this is your P by FCK equal to 1.5 by 0.08. Now what about your PU? PU equal to 1200 kilonewton, and PU by FCK BD equal to 1200 into 10 to the power 3 divided by 20 times 400 by 500, which comes as let us see how much is coming. So 0.3. So PU by FCK BD is coming 0.3 and P by FCK 0.08, D dash by D 52.5 divided by 500. One case D dash by B also will be there. There will be two cases. So 52.5 by 500, 0.105. So let us just summarize the whole thing. D dash by case 1, D dash by D. We can talk about, say, one about major axis, another about minor axis. In that case, I can say 0.105 PU by FCK BD equal to 0.3, P by FCK equal to 0.08. And so MUX1 divided by FCK BD square. How much will be MU? We are talking that about, say, major axis. So about D we are talking. So MUX1 by FCK BD square we are talking, say. And X we can always talk, say, your major axis. So if that be the case, our D dash by D equal to 0.105, use chart for D dash by D equal to 0.1. So that one comes in chart 44. This is your chart 44 and your PU by FCK BD 0.3 and 0.08. So which is coming as, so 0.1, 0.11, 0.12. So that one it comes as 0.12 from the chart. What I am doing here, please note, I am doing here that there are so many starting from 0, 0, 0.02, 0.04, 0.06 P by FCK. What I am doing, PU by FCK BD is 0.3. PU by FCK is 0.3, so I am going along this, and then wherever it is cutting that curve of P by FCK 0.08, then I am coming down. Okay? So when I am, and then I am coming down, and then I can get where it is cutting here, it is cutting here 0.12. So this is the value. That means, in other way, if it is uniaxial bending, if it is uniaxial bending, then whatever I have chosen, so I shall get that curve, say P by FCK 0.08. So what I am doing, PU by FCK 0.3, so I am coming, moving like this. Okay, for your sake, at least let me spoil my book also at least. So I am coming here, okay, and then I am coming down like this. Is it correct? So this is the thing what I am doing. So I am going, so I have started here, PU by FCK BD 0.3, then P by FCK 0.08, this curve, and you come down wherever it is cutting cutting at MU by FCK BD square, that is your 0.12. Okay, so that value we have taken, and that is we have taken from D dash by D equal to 0.1. So that MUX1 by FCK BD, which is coming as 0.12. So what is the value of MUX1 then? Equal to 0.12 times 20 times your, what about the 400 times 500 square. So 500 into 500 into 400 into 20, 2.12. So 240 kilonewton meter. Similarly, I can try for the other one. So, number 2, d dash by b. D dash by b will be equal to 52.5 divided by 400, because I am taking about the other axis. Let us say that is the minor axis. So 52.5 divided by 400, 0.13125. So choose d dash by d equal to 0.15. I shall take that chart where d dash by d equal to 0.15. Pu by FCK BD, there is no problem, it will be same, 0.3 only, there is no change. P by FCK also there is no change, 0.08. MUY1 by FCK DB square, that one we shall get it, and where from we shall get it? We shall get it from the chart 45. So we are getting from the chart 45. So 0.3 and come down 0.11. So the value is 0.11. 0.3 I have started and then I am coming down here, so it is 0.1, and you will get it in chart 45. Okay, so SP16, chart 45, page 130, and this is 0.11. So MUY1 equal to 0.11 times 20 times 500 times 400 whole square. So let us check 170. Shall I accept it? 176 kilonewton meter, right? Okay. So MUY1, that is a 176 kilonewton meter. So we know MUX1, we know MUY1. What about PUZ? What about PUZ? So PUZ equal to 0.45 FCK AC plus 0.75 FY ASC equals, this one you will get it again, clause 39.6, page 71, IS 456 2000. So 0.45 times 20 times 400 times 500 plus 0.75 times 415 times P. How much we have chosen P? P equal to 1.6. So 1.6 by 100 times 400 times 500. So this much is your area of steel we are getting it here, and we should not stop it here because we shall get it here again. How much will be that one? Minus 0.44 or 45, let us say is 45 FCK times, or 45 times 20 I can make it, times 1.6 by 100 times 400 times 500. I am just subtracting the portion because already I have taken the full one. Either AC will be equal to, if you would like to make it very clear, the other way also you can make it, this portion you can omit it. So let us find out AC. AC will be equal to 400 times 500 minus 1.6 by 100 times 400 times 500. This I can do it. because this is the one that exactly the area of concrete. So 1.6 by 100 into 400 into 500. So area of steel is equal to 1.6 by 100 times 400 times 500 equals 3200 square millimeter. This one comes as so 400 into 500 minus so 196,800 square millimeter. So either you can do it here, this portion you can just simply write down, or you can deduct the portion, whatever way you feel. The same way I am doing the same thing. So what I can do it here then, let us make it PUZ. I have calculated, so 0.45 FCK times AC plus 0.75 FY ASC equal to 0.45 times 20 times 196,800 plus 0.75 times 415 times 3200. So 0.45 times 20 times 196,800 0.75 times so 1771200 plus 175 times 415 times 3200 9960. These are all in Newton. So plus 1771200 2767200 Newton. Okay, which comes as 2767.2 kilonewton. So PUZ equal to 2767.2 kilonewton. What about your PU? PU equal to 1200. PU by PUZ equal to 1200 divided by 2767.2 equals 0.433 alpha n alpha n equal to 1. Okay, let me do it in the next page. So PU by PUZ we have computed 0.433 for PU by PUZ equal to 1.0 alpha n, sorry 0.2, this is 0.2 alpha n equal to 1.0, PU by PUZ equal to 0.8, alpha n equal to 2.0. So alpha n equal to 1.0 plus minus 1 times 0.433 minus 0.2. So how much is coming? So 0.233 divided by 0.6 plus 1. So 1.388. Okay. So we have got that alpha n equal to 1.388. So let us now summarize the thing. So what we shall do it here, PU 1200, let me come to that portion where I have missed those values. Yes. Pu equal to 1200 kilonewton, Mux equal to 100 kilonewton, Muy equal to 80 kilonewton, Mux1. How much you have got Mux1? 240 kilonewton meter. Sorry, this one all meter, kilonewton meter. And Muy1 176 kilonewton meter. I think I am going out of paper. Okay, Mux1, Muy1, and Puz 2767.2 kilonewton, 2767.2 kilonewton. So we can, and alpha n computed equal to 1.388. So Mux by Mux1 to the power alpha n plus Muy by Muy1 to the power alpha n equals Mux equal to 100 divided by 240 to the power 1.388 plus 80 by 176 to the power 1.388. Let us find out how much we are getting. 100 divided by 240 . So first part I am getting here 2.2966 plus 80 divided by 176 . 0.33447. So we are lucky. 0.2966 plus 0.3347, which is coming as 0.6313 less than 1.0. So that means the section we have chosen that we can, at least it is safe. We cannot say it is economic, but at least we can say it is safe. So we can reduce the section and then also we can try and we can find out that whether we are we can find out that section. So that means whether we can make say little bit less, say instead of making 450 we can try say 350 by say 450, like that we can try and we can find out. So this is the thing that we do it, say your biaxial bending. So we know now axial loaded column, uniaxial bending, biaxial bending using this SP16 the chart extensively. So far we have done the slab as well as say beam, that we have done as far as possible we have used formula, but here we are extensively using that say chart. Other alternative obviously that you have to do it, that lot of calculation you have to do. One more thing I would like to tell, that how shall we make this interaction curve. The if one can do that one say adventure making the whole SP16 your say as say one can make it say computer aided, whole the chart and tables, all those things they can make it, or other way one can make it say whole thing that concrete design you can make it say computer aided. Now here what we do it, interaction curve particularly, I do not go this curve say on the basis of this interaction curve. What I do actually, I do it directly, I make my, say this is the section, let us say 300 by 400. I do not go the percentage of steel. Why shall I use the percentage of steel? Instead of that, I prefer that okay, let me try with say 4 number of bars, say 425 torr, maybe a little more also. Say like this we can provide. Then what we can do, or 6 we can provide, say 625 torr, or if I provide say here all sides 825 torr. That means I am directly, when I am doing the computed design, but then why shall I go with this non-dimensional one? Here they are using non-dimensional. That means so that with the minimum number of charts or tables, they can use as many design as possible. That is the whole objective. But when you are doing that computer-aided design, that means you are using computer. So in that case, why shall I go again non-dimensional? Instead of that, I prefer that, okay, I would like to provide this section. Whatever area of steel is coming is fine. So that means here, in this case, P will be equal to, if I take say 4 numbers, 425 torr, then 4 times 491 divided by 300 by 400. Am I getting the minimum reinforcement? Let us check it first. That one also required. Okay. So P equal to into 100, let us make it, then it will be clear. So 1.6%. Okay. So when we are getting this 1.6% the area of steel, I prefer that, okay, let us use this one and find out that interaction curve and then check whether we are it is safe or not. Because I don't prefer that P by FCK, all those things. Directly I can get it and I can find out. Another one here, and also if I use say M20 grade or say M25 or M15, I can use that grade also, that steel, because in this particular chart they have used that M20 grade all along. For preparing the chart, wherever they need that one, say your FCK value, there you have used that, you assume that they are using concrete grade say M20. But that is not the case. So what I can do when I am doing the computer design, so I shall obviously I shall use that one also, that whatever grade of concrete you are using, so let us use that grade itself. So that way we do it. Not only that, what we do it, we can do it for circular column also. How do we do the circular column? What we will do, the same fashion you have to do it. Same fashion you have to do it. That means the maximum compression side, and this is your maximum compression side, say. What you have to do it? How shall we get this one? I prefer that let us take a small strip, maybe 5 millimeter, maybe 10 millimeter strip. That means each of them could be, one can make it like this also. This is one rectangular one, which may have this one. Other one may be something like this. Other one may be say something like this. So like that it can happen. Maybe you are having this one bar here. Maybe you can have one bar here, 2 bars. Like that it can go. The same circular section, I am doing it as a rectangular one. So like that I can do it. So this is the one, that circular one, you can make it the way, so as if this is like this, one can do it also this way also, hexagonal thing also like that also one can do it. Say something in this way I can do it. If you would like to make it trapezoidal, the whole circular section, that one you are making it as a trapezoidal section. That means in a hexagon or in a polygonal form like this, because it is not possible to make it your say whole that circular one. So what I can do, I can take a section as if the section is like this. If we can find out for this, then I can provide it for any one of them. This is the one that we can do it. That means it is more closer to the one circular one instead of having this one. That means in this case, if you can develop your say for rectangular one, you can do it for the circular one also, that you are doing that equivalent section in this fashion. That means modeling the circular section in this fashion. Whereas if you would like to little bit more adventurous, then you can take it say your trapezoidal one, which will be more closer to the your circular section. So this way that you can make your own design. Not only that, you can take a section say like this, the column is like this. So which is nothing but this is 3 rectangular. So I can take this one, this is another one, this is another one, 3 rectangular, and each of them are stressed at different level. Not only that, this one at say highly stressed level, this one in the middle, this one at the end. So for each of them you have to find out that what is the moment capacity and what is the axial load capacity. The moment capacity always we take it with respect to this point, with respect to this line. If we take that means say from the maximum stressed one, or we can take it with respect to say neutral, that say mid section also, that also we can do it, and then we can find out that you say what is the moment capacity, all those things. So this way we can do it. Not only that, one can do a section say it goes something like this. The section goes, I am sorry, little bit coming complicated, but this section may come like this. Whenever the section is coming in this fashion, then what we can do, that you have to design. What you have to do, again you have to find out the same strain diagram as if you are having this with the maximum stressed. So I can find out the what is the maximum stress and this is the minimum stressed, and I can find out the again interaction diagram for this curve. In fact, actually when I started this interaction curve, when I got this type of problem, industrial problem, then I thought, okay, let me do my own, because nowhere I cannot do anything using say SP16. So I have to make my own. So then I started finding that how can we do it. And not only that, there is further possibility that as if it is like this, and then we are having the section, it goes in this fashion. So if the section say hollow and also you are having little bit say stiffener, you can say this one, the column is going like up like this. So now you have to do it. That means here not only that there is one rectangular portion. So if I see the stressed model, whatever here, the neutral axis is somewhere here. The strain is here. Neutral axis is somewhere here. What about the stress diagram? The stress diagram, I can, if I plot it, it may come say something like this. Now you can imagine that certain portion here, certain portion here, certain portion you have to remove it, certain portion here the rectangular one, that means this is your rectangular one, this is another rectangular, this is another rectangular, this is another rectangular, and all the your reinforcement along the periphery, say you are giving all the reinforcement along the periphery and also including here also. That means the not only reinforcement here also. And reinforcement along this. So that means so many reinforcement you are providing. So for each and every component you have to make it, but that itself you can do it using only rectangular and circular. A rectangle that is placed here, what is the strain diagram, what is the stress diagram, you find out that portion, you individually compute that what is the moment capacity and what is the axial load capacity. For this section you find out, for this section you find out and remove it, subtract it. Similarly for this one also. So wherever you have the stress diagram, that means if you can understand the stress diagram and strain diagram of that, say your limit state of method of say concrete design, immediately you can find out, and we have always find out the moment capacity, axial load capacity. So all those things you can find out, and that's what we are doing here, and it is very simple. That 0.0035 and 0.002, these are the different strain, and on the basis of that you can find out. So what I mean to say, in all along, that apparently it may look like say very complicated, but it's not so. One can design your say own thing also, your say with the computer aided, it is very easy. So also at the same time, one thing I don't like, the software whatever available in the market, that is very say software available in the market, that one as if it is a magic box, but that's not the case. Because sometimes we find very difficulty, they come to us and tell us, okay, this is the result, I have got it, and you have got it from software. Now another problem it comes, that how do we check it? Because you have to check it, those values, whether it is coming all right or not, because you do not know what method they have used, what they have done, that we do not know. So that way also, actually for that purpose I started developing this software, that you would say one thing. But here one thing what I am trying to do, that is not a magic that I would like to prove. That means here it will also give the step by step that your results. It's not the one only that, okay, let us provide 10 numbers of 25 torr bar. Okay, that's fine, but how you have come to that level? If somebody is interested, he will be able to see that all the information, okay, this is the clause, this is the result, all those things, and that is very important. And I personally feel that it should be supplied in that fashion, not as a magic box what is today now. Anyway, we shall continue, and after the in the later part I shall give all those things in the computer aided design part. Okay, I think we shall conclude here. Thank you.